All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully you guys are doing well, had a good weekend. We have some problems to get into, so let's just actually get into those. Let's make sure I can see the chat here. Don't do that. You're gonna make me yawn. Yawns are contagious. It's early. I know. It's been a long weekend for me too. But we're all here. We're surviving. Okay, so it's been a weekend, so let's just do a quick crash course recap of what we've been talking about. We've been talking about limits, and there's a very specific mathematical definition of limits, but we are not concerned with that. We're more concerned with the intuitive definition of limits, which is basically what the y value gets close to as the x value gets close to something. So we say that the limit as x approaches a of f of x equals L if, as x gets close to a, the y values will get close to L. And it does so uniquely and unambiguously, right? So that's what a limit was. We did some examples with this guy. As x gets close to 2, you can see that our y values get close to 5. In this scenario, you realize that you could actually plug in the x value and you would actually get that answer, which is pretty cool. However, you can't always do that. So here was an example where we couldn't plug in the 2, but we still could figure out what the limit is because of the definition. When you get close to 2, the outputs get close to 4. And we could figure that out from the graph as well as by simplifying stuff. Here was an example of where we approached 2, and there were 2 different answers for what the limit approached, which just wasn't good enough. So for our definition, it had to approach the same answer from both sides in order to exist, as we call it. So this was a case where it does not exist. Moving on. Going back to more examples. However, that last example felt kind of cheap because if the limit is all about tracking the y value, then clearly we could have tracked the y value here. And it's just because you forced us into this weird definition that we had no answer. So what we did was we invented one-sided limits, where we can talk about limits coming from one side at a time. And that way, we could actually describe in enough detail, at least in as much detail as a limit would want to describe what is happening in this situation. So although the overall limit does not exist, we had our one-sided limits existing. And when we come from the right, our value is 7. If we come from the left, our value is 0. These are talking about the one-sided limits, limit from the right and the left. And those individually had answers. However, because their answers did not agree, we take the existence of the overall limit to not be a thing, right? So the overall limit will only exist if both of the one-sided limits exist and they are equal. There are also various scenarios for existence and non-existence of the one-sided limits and the overall limits. One thing is for sure is that this guy is not going to exist if these two guys don't exist and they don't agree. Otherwise, you can mix and match all sorts of stuff here. So now, yes. Now we went on to more examples, and we started looking at some examples where infinity started happening in the mix, right? This one ended up not existing. This one ended up existing and being infinity. We also looked at limits where the x value approached infinity, and we learned how to deal with those. And these brought up the notions of limits involving infinity. There were 2 main types for us. Infinite limits, this is when the answer is infinity, as well as limits at infinity. And this is when the input is approaching infinity. And of course, limits can be both. So this is an infinite limit at infinity. And yeah, that was an example of that. So these are how we can talk about limits at infinity. And we went through what that would actually look like. We then spoke about the properties of limits. We learned that limits were actually very nice property-wise. All the things, all the mathematical tricks that we are used to so far, we can do all of them with limits. Limits, you can factor stuff out. You can distribute across sums. You can distribute across pods, distribute across divisions. Pull inside of powers, pull out of powers. It's crazy how many things that limits can do. It's very, very super rare that we have a mathematical operation that can do all of these things at the same time. In fact, I can't really think of another one where this is actually true for that you would have seen before calculus class. Yeah, so multiplication doesn't work like that. Exponentiation doesn't work like that. Division doesn't work like that. Distributive law doesn't work like that. Like, what else works like this? Nothing, right? Limits are really nice. They're really very nice things to work with mathematically. Then we spoke about strategies for computing limits because, yeah, we could go through and we could get limits by these answers with all these fuzzy, well, you see what's happening with this picture, but really, we want a very quick way to compute limits. So I gave you a list of strategies. So step one, you see a limit. What do you try to do? You try to plug in, find the answer. This will work on the very nice limits right here, like the very easy ones that, you know, if I give you a limit like this, sure, there'll be 1 and 2, but it's not going to be most of the limit problems that I ask you because that one's just too easy for us. That's like evaluating a function, which we're very used to from pre-calc. The second step would be to, if we can't just directly plug in and get an answer, to actually simplify so that we can plug in and get an answer. Simplifying does not fix the domain, but it does put us in a convenient situation for finding limits. So while simplifying doesn't actually fix the hole that was there before, it now makes it easy to know what position that hole would have been in. And that is more what the limit is concerned about. What are we heading towards as the x gets close to 2? So that was the second strategy. Applying a special technique is also another strategy. We're going to look at one of those today. Well, maybe a couple today. Graphing or table of values is also a nice strategy. Whenever it's possible, I would say graphing is the better one. But table of values is another one. However, it's not great for us because it's very computationally intensive, and you know, I expect you guys to do all your calculations by hand, so that's not great. But by looking at the picture, we'll know how to get to the answer. But you can actually also fill out a table of values by making sure you're plugging in values that are getting super close to the thing that you're interested in. For example, here, we wanted to find the limit as x approaches 0. So we don't know what x approaches 0, what the limit is. So what we do is we approach 0 by plugging in numbers that get closer and closer and closer to 0. And I don't just mean plug in numbers like, okay, we're going to plug in 1 million. Now we're going to plug in 500,000. Now we're going to plug in 10,000. No, super duper close to 0, right? 0.0001. Those are the kind of numbers we want to look at. And then we examine what the outputs are doing, right? And try to see, can I see a pattern? What are they heading towards? What are they doing? And as we can see in this situation, if we're coming to 0 from the right, which is above, the number just keep getting bigger and bigger. So we describe that as infinity. If we're approaching 0 from below or from the left, then the numbers keep getting more and more negatives. We describe that as negative infinity. They just will keep getting more negative. They don't really head towards anything specific. Because these guys did not agree in our table, we know that the limit does not exist, right? So that's how you can use table of values. But it's pretty much one of the last resorts. It's one of the last things I would actually try to do. Step 5 would be to use your knowledge of the behavior of functions, which we talked about. And we're going to talk about that a little bit more in the next class, I think. But so far, here are some things we know. So far, we know this for sure. Logs grow slower than polynomials grow slower than exponentials as your x is going off to infinity. This is so drastic to the point where guys on the left are effectively 0 compared to guys on the right when your x is getting very large. And that's super important. That's very convenient. We haven't discussed these functions yet, and I don't think we will. That's more of a Calc 2 thing where you deal with these guys, but I just thought I'd just throw them in just for good measure. So this guy's called the factorial. This is the variable exponential. But they grow even huger compared to these guys. However, using this kind of knowledge, we can now judge things like limits at infinity. I know that if a polynomial is fighting an exponential, the exponential wins. The polynomial is effectively 0 compared to the exponential. And so we have essentially 0 divided by infinity here. And that gives us 0. This notion is called bottom heavy, not a technical term, just a Jhevon term, so that I know that you know what you're talking about when you look at this and you give me an answer. Similarly, if the situation was reversed, we have an exponential versus a polynomial. Polynomial, effectively 0. The exponential is going to get huge. This is effectively going off to infinity over a very small positive number. That's positive infinity, right? This is what we call top heavy, when the numerator overwhelms the denominator. Okay. In light of the above strategies and properties, then, we actually won't need to use the, well, we did use the properties there, but in light of those strategies, I gave you a whole bunch of problems to try, and let's actually do those. So that's what we were going to, that's what we're going to do now. And then I'll introduce you to some special techniques. For the most part, we're going to wrap up limits today, as is the plan. But I will come back and teach you guys another special technique later down the road. I don't know, 2 weeks from now, something like that. Okay, so that's where we are now. Okay. And that has been the recap. I asked you to try these last time, so now we're going to jump into it. Time permitting, we'll jump into continuity as the next topic, but I mean, am I going to want to start that? I don't know. Let's see how quickly we get through these guys. So we're going to do these guys. So the first one is this guy, and we are ready to officially begin. All right. So what's the answer for this one?
1/2.
Got a half? How?
Well, I had factored everything and then like plugged in, but I realized you didn't really have to factor, because if you plug in 1, it's not going to be 0. So you can just plug
right,
in.
But how did you factor before?
I factored, so I factored the x squared plus 1.
Into?
X squared plus 1, x plus 1, x minus 1. And then I canceled the x minus 1.
Yeah, but is that true though?
Oh, is it not? I guess not, because it's x.
It's not, right? Because that's this gives us what? What is that?
0 then.
This is x squared minus 1. That's difference of squares.
Yeah. Wait, I just realized that.
Yeah, yeah. Jhevon is tricky, man. That dude, he's gonna write stuff to make you think. But yeah, there's a plus sign, so yeah, we can't do that. Does not factor. Well, it does, but you'll need either complex numbers or a huge ton of radicals where it's not worth it at that point. It's not really simplifying at that point. Does not factor for us. Right? That's the sum of squares. We don't have a rule for factoring the sum of squares. Okay. But you're right, you did not have to factor, because if you plugged in the number, you don't divide by 0. And so what I would do is simply just plug in 1. And if I plug in 1, what would I get?
0.
You would get 0, yeah. Right? Which kind of tells you that, wait, I got a half when I factored, something must be off, right? So it's actually 0. Yeah. So that one was one of the easier ones. You'd plug in. You didn't have to do anything. And there are times when you don't want to factor when you don't have to. So again, what I would highly recommend is that you remember to follow the strategies. Remember, grasshoppers. Follow the strategies. Because there might be something, and I'll give you a very silly example here, but there might be a time when I would give you something where, yeah, you could go in and factor stuff and rewrite things, but it wouldn't it wouldn't help. So you end up wasting your time. So I could have asked you something like this, right? So x minus 1 over x squared minus 1. And sure, you could factor and simplify, but that would actually be a waste of time, right? So you could yeah, I could, it wouldn't be wrong, but I could go, oh yeah, and this is going to be x minus 1. I'm going to see that as difference of squares. So this is x plus 1. This guy's going to cancel. That's going to leave me with x that's 1 over x plus 1. And now I'm going to plug in the 2, and then I'm left with a third. But the thing is, you could have just plugged in from the very beginning, right? Right? So this is easier. And by the way, this would be step 1. This is step 2. You shouldn't be thinking about step 2 before you think of step 1, right? So just because something looks like it's going to factor does not mean you should go and factor it. Worst case scenario, you get it wrong because you factored incorrectly or something else went wrong. Or best case scenario is you're going to waste time factoring and simplifying stuff when you didn't need to, right? So the strategies that I gave you, I wrote them as steps because I specifically actually want you to think in that direction, right? You should be looking to plug in before you look at factoring. So when you look at this one and you see x squared plus 1, it's, first of all, it's a trick, right? Like it doesn't factor. I just wrote it like that because I knew some people would fall for it. And then, you could get in trouble that way. But even if it could factor, that is not the first thing that you should think about. Plugging in is the first thing you should think about, always, right? Because I could give you stuff that would factor and it would just take a long time. Like if I had an x cubed plus 1, sure, that would factor. But again, does anyone even remember how to factor the sum of cubes? Well, you should. I kind of expect you to, by the way. I don't know. Is that unreasonable? I don't know. Yeah, but like x cubed plus 1, that factors into x plus 1 times x squared minus x plus 1, right? And that could lead to all sorts of things. Like if you don't have to do that, dealing with this version instead of this version when you really don't have to, it makes your life harder, right? So there's a reason for the strategies. There's a method to the madness, right? I know I seem crazy, but like nothing I say is random, actually, regardless of how it might look, right? So I gave you the strategies, I gave you the steps because that's how you should be thinking about them. And even if doing something else could get you to the answer, chances are it'll be harder and take you more work to get to the answer than had you followed my strategy. Okay, so yeah, lots of lessons we can get out of the first one. Let's move on to the second one. Okay. All right, what do we do here?
You can't plug in.
You can't plug in. Okay, good. All right. So I was going to see if the first thing someone said was to factor. Plug in should be the first thing you think about. So you see a random limit problem, right? So again, I'm writing in blue because this is not something that you'd write on paper, but I do want you to be thinking in this direction. So you see this, the first thing you think in your brain, plug in, right? And then you're going to realize, can't plug in. Right? Because it's like division by 0. Right? Now you start to think about something else. The second thing you would think about, simplify. Right? So can we simplify this?
Yes.
Yeah? What does it simplify to?
was like a difference of squares.
Mm-hmm. So that's in the bottom. What does it become?
Well, to make them equal, I kind of combined two steps here, and I pulled the negative so that it'd be x squared minus 1.
Okay.
And then I factored just so it was easier to cancel.
That's fine. That saved me some time because I was gonna, if you didn't do that, I was gonna ask you, well, how are you gonna cancel? And then the trick would be to pull out the -1 later, right? So, okay, you dealt with that in the beginning. So yeah, now we're good. So yeah, you can cancel these. And we're left with limit as x approaches 1, 1 over, well, minus. And so now what?
You plug in the 1.
Now we can plug in. That's minus half. Again, notice I keep writing the limit symbol until I actually take the limit. I mentioned this last time, but it's worth repeating. Keep writing the limit symbol until we take the limit. Okay, so notice that while I'm simplifying, I'm writing the limit symbol because I'm not actually evaluating the limit yet, right? I evaluated the limit on the last step. Now I know what the answer is. There's no reason to write the limit anymore, right? So it's not like I'm asking the question, what are we getting close to? It's like, now I know what we're getting close to. It's minus a half, right? There's no reason to ask, what are we getting close to anymore, right? So, but until then, we're that's the main question. Okay, so that's it. So the first thing you do, think, can I plug in? Oh, doesn't work. Next thing, can I simplify so I can plug in, right? So that's all. That's how we're thinking about these problems. Right? It's not just about getting through them. It's about efficiency. Right? All right, what do we do here? You go, can't plug in. 2, simplify. Can it simplify? There are times when I'll give you stuff that might not simplify, but can this one simplify? Well, yeah, it is a difference of squares in the bottom.
But that doesn't help you.
Does it not? Would Jhevon do such a thing to us?
Yes.
Apparently, like, yeah, damn, you can't trust that dude. It's like 8:30 in the morning and he's doing like what? But now, so we did simplify, but still can't plug in, right? Now what?
Right? Is that the third step?
Yeah, so what's the third step?
Graph? Or
Well, almost. The third step was special technique, but I didn't tell you any yet.
Yeah,
so,
you haven't told us any.
So special technique, but Jhevon ain't tell us yet. So now, yeah, we move to the fourth one where it's like a graph or a table of values. And as I mentioned, I'd rather the graph, especially for something like this, the graph of 1 over x minus 1. You should kind of know what that looks like. What does that look like? What does the graph of 1 over x minus 1 look like? Anyone? Bueller.
Would it be the graph of 1 over x, but it's shifted towards the right?
Yeah, right. So it looked like 1 over x, but shifted 1 unit to the right. So you'll notice that this is going to be that. However, shifted 1 unit to the right. So the graph here looks like okay. So now that we know the graph, what is the limit here?
Infinity.
Hello?
Infinity? Hello?
Yes, I can hear you. Your audio is very low though.
Oh, I'm sorry. I said infinity.
Yeah. Infinity. Let me make sure it's not a problem on my end. I was hearing the others okay, but you're kind of low. Let me turn this up in the settings. So infinity, we agree? No, you're shaking your head. What's the problem?
Well, you have to look at it as it like approaches 1 from each side.
Mm-hmm.
So you'll be approaching 1 like from the negative side, from the positive side. And if you
Okay, so if I take the limit as I approach 1 from the right side, what happens?
It's positive infinity.
And the left?
Negative. So the limit does not exist.
Does not exist is the answer here. Okay. So be careful. Remember the limit, you can't have any ambiguity. You check from both sides. Clearly the graph behaves differently on either side of the line x equals 1. So you should really take care here. Now, I'll show you the other way you could have approached this, although not recommended. So you could have just shown me that you drew up a table where you're looking at x and y equals 1 over x minus 1. And obviously we want to get to be a level 1. So we can approach 1 from above or to the right, from the right as if you're looking on a graph. So you could do something like, 0.9, 0.99, 0.999, 0.999, right? And then we go over here and we'd actually plug that in, 0.9 minus 1. This is actually from below. This is from below or left. Okay. And then you have that. And so what's going on? Here you would have 1 over 99 minus 1, 1 over 0.999 minus 1, 1 over 0.9999 minus 1, right? Now, what these actual values are, I mean, you'd have to calculate that. You could do something like think of the 0.9 as 9 over 10, and then the 0.99 is 99 over 100. But the idea is, you'll notice here that the denominator keeps getting smaller, and it's also negative. So notice that this here is a positive number divided by a negative number. And that's always going to be the case. You take 0.9 or something like 0 point something, and you subtract 1, you're going to get a negative number. So clearly, the denominator is getting smaller, and the fraction is continually negative. So what's happening here is that as we're approaching negative infinity as we come from this direction. But if that's not clear, you'll actually plug in the values into by hand or by calculator and then do that. Another thing you could have done, well, it's 1.1, 1.01, 1.001, 1.0001, right? And so now we're approaching 1 from the left. And again, we don't know what this limit is. So this is from above. Should have done this in the top parts of the rows, but the 0.9 came to my brain first. So, or right. Right. And so here you're gonna have that. Then you're going to have that. Then you're going to have that. Then you're going to have that. All right. So you realize that this is giving you like 1 over 0.1 and 1 over 0.01 and 1 over 0.001 and 1 over 0.0001, right? So the numbers are getting smaller in the denominator, but they're staying positive. So coming from this side, you'll realize that this is approaching positive infinity. Then you realize these two guys don't agree. So that tells you the limit does not exist. Right. So again, you could get to the answer that way. I would not recommend it though, because time is of the essence. Right. And this is like not even with me actually figuring out what the answers are. I'm just looking at the pattern of the fractions. If you couldn't even, if you're in the situation where it's even hard for you to actually judge what's happening to these fractions, noticing that the denominator is getting smaller, and so that means the number is getting bigger, then you're in more trouble. You'd have to actually do more work than I just did, and that already felt like it took forever. So yeah, but you should know, oh, this is just like the graph of 1 over x shifted to the right. So draw it there. Oh, they do different things. Done, right? And you move on, right? So yeah, so here was one where, yeah, try to plug in, can't plug in. Simplify, didn't really solve our problem. So now we move on to the big guns. 3 was a special technique, but we don't have that yet. And 4 is to actually graph or do a table of values. The other technique wouldn't really help us here because we have 2 of the same kinds of functions. We have a polynomial on a polynomial, and the x isn't like going off to infinity or anything, so it doesn't really help us. Ooh, interesting. Well, that's an interesting example. Kudos to the guy who picked all these problems. These are very interesting problems. Okay, what do we do here? Same thing we always do. You try to plug in. Same thing we do every night, Pinky. Try to plug in. Can't. Right? Literally have a division by 0 right off the bat because there's an x in the denominator. So 2, simplify. How do we simplify that?
It'd be like plus or minus 1 because like x over x is 1, but you have the absolute value, so it's like...
So how when is it the plus? When is it the minus? How do you apply that?
That's why like I graphed it.
And what did you get for the graph?
It like approaches 0 from like the positive side at 1, and then from the
Uh-huh.
negative at -1. So that doesn't exist.
Right.
That's what I did.
So, okay, and I'll do it that way. So let's also do the simplification. So when it comes to simplification, sometimes it's not exactly obvious what to do. And whenever that's the case, you go back to basics, you go back to the definition. So here you would just recall, what does the absolute value of x actually mean, right? So for us, we know it's a piecewise function, right? When our x is positive, it's that guy, it's 0 if x is 0, and it's minus x if x is negative. Because if x is negative and I take a negative of the negative, it makes it positive, and the absolute value is going to keep things 0 or bigger. So that's the definition. And so this means that if I have absolute value x over x, right, this means, let's keep the limit. If I have the, yes, this would be something that you wrote right. So let's put that in different color. This means that if the limit as x approaches 0 of absolute value x over x, then I know what that really means is in one situation, namely when my x is positive, so I'm only looking at the right side of 0, my absolute value returns x itself. It does so when x is larger than 0. Now, here, it makes no sense because you'd put in a 0 in the denominator, but the limit doesn't care anyway, so it doesn't even matter. So here it makes no sense. But limit no care anyway. It's a honey badger. And then here, when we're negative, absolute value gets replaced with negative x. So then you're going to realize, oh, this guy's going to simplify to 1 if I'm on the positive side. And it's going to simplify to -1 if I'm on the negative side. Now, what is the limit as x approaches 0 of 1? Right, what is the value here? What is that limit value?
One.
That's 1, right? How do we know? Well, I went through this whole system, I graphed it. No, that's not what we do. This is straight up one of the properties I gave you guys last time. Property, limit of a constant is the constant, right? You don't have to do anything, right? You don't need to go through a strategy for that. That's like straight up one of the answers we know. So if you're taking the limit of a constant, it's just the constant. So the limit of 1 is just 1, the limit of -1 is just -1. But now the issue is, don't agree. Okay, so does not exist. Okay. Now, admittedly, this would be the way that I would tackle it. But admittedly, I think this is the kind of thing that a lot of students just wouldn't think of doing. Although that's probably because they would have forgotten what the exact definition of the absolute value is and how am I going to get this in there. So the graphing would probably be the more intuitive thing. So admittedly, a student may not know how to do the above. So graphing is probably more intuitive here. So the idea would be, so alternatively, but the idea is you can't really get away from the definition of the absolute value though. You're still going to need to know that it's positive x one way and negative x the other way so that you could even get that graph. Again, in light of the definition, right? But sometimes even knowing that definition and knowing how to actually write something down mathematically and express your thoughts mathematically, that's a whole other skill in itself. And that might just not be something that we are comfortable with at this point, which is fine. So if you don't feel comfortable with that, you just move on to the next stage of the strategies, right? And you just keep going, right? So I did say, you know, it's about efficiency, but really, if you can't get to the answer in the most efficient way, just move on to the next most efficient way. You know what I mean? Like, don't be stuck. Well, you know, I want to do this problem in a clever way so that Jhevon is impressed. Like, no. You don't see how to do it with a step 2 strategy. Move on to step 3. Don't waste your time, right? So a lot of people this might totally confuse them, but they might be able to handle the graphing a little bit better. Just move on and do the graph. Like, you're not going to get downgraded for that, right? So as long as what you write out, it makes a logical mathematical sense. It's a very coherent thing. You're making, you're thinking mathematically. I can see that, oh, it makes sense, their thought process. You don't just randomly come up with an answer. It's cool. So here, you would know that if you look at y equals the absolute value of x, so the first very typical thought is that a student might think, well, that's just plus or minus, isn't it? Which in some sense, yeah, but it's not specific enough. Specificity is actually super important in mathematics, right? So especially when it comes to definition. So don't just say something's plus or minus. The absolute value applies the plus and minus in a very specific way. So what you should realize this is, well, it's a plus specifically in this scenario, and it's a minus specifically in this scenario, right? Better. Right? And this is also better because I could have asked you a one-sided limit, right? I could have asked you just the plus side, right? And you would really need to know, well, which side should get the plus, right? So you always want to, when you're applying a definition, you need to know it exactly, you need to know it very specifically. So now we can know, okay, so that is basically going to look like, well, 1 if my x is larger than 0, -1 if my x is less than 0. And so now you can just go to the graph. And of course, you should know what the graph of 1 and -1 look like, right? So that's at 1, which is just a horizontal line, and -1 on the right. And clearly from that, you see the right and the left don't match up. And just to explain a little further here, that's because since the limit as x approaches 0 from the right of absolute value x over x is 1, but that is not equal to the limit as x approaches 0 from the left, which is -1, right? So the left and right don't agree, and so the limit does not exist. Yeah, I'd say if I were a betting man, most students would actually, most students who could get through this problem would get through it the graphing way. If you saw this problem and you did it this way, I would probably recommend that, yeah, you should have been in the regular calculus, not the applied calculus. but then you probably don't have to be depending on your major. Who knows? So if you're in like biological sciences, or you're dabbling in calculus, you're curious, but you don't really need it, it's fine to be here. I mentioned that on day one, like the calculus 1206 is meant for a certain kind of major: math, physics, chemistry, engineering. Here's where we're for biology and all the other people who kind of nominally need calculus. 1109 is for business majors. Here's another one, right? So limit as x approaches 0 of this expression. Okay, so what do we do? Well, looks complicated, but let's try to plug in, right? Because that's step one. Can't do it. Just can't do it, Captain. Why? Because in the denominator, if I plug in 0, I would get 1 plus 0 minus 1. That leaves me with 0 over 1 minus 1, which is 0 over 0. Lightning strikes. Like, even writing this is an offense punishable by death. So we're not even going to talk about that anymore. So now we're moving here to simplify. Can we simplify that guy? Ideas on how to simplify that? Can it be simplified?
Honestly, I have no idea. This is the only one I couldn't get.
Yeah. Maybe it's a trick. Maybe it can simplify. And really, we're just supposed to be plugging in values here.
It doesn't look like you can simplify.
Because, yeah. But, I mean, so plug in values. Like, would you want to plug in values into that? Like let's go and plug in point 0.0001 into that guy. Like, it's not a fun time, right? Does Jhevon really expect us to do that? This one does simplify. Does anyone see how, though? It's something you just have to remember. It's one of those things for those who know, you know. So it's one of those things from algebra class that we have to remember.
You got to do something with the denominator.
Yeah, the denominator is the problem. But what? What do we do here? Anyone? I mean, like, what's making this annoying to simplify? Like, what's the thing in the denominator that's bothering you?
The square root.
The square root. Okay, so we have a sum, right? So a subtraction of things, and one of the things is a square root. Is there a way that we can get rid of that?
Square it.
I see where you're going, but no, right? So you can't just randomly. It's like bummer. You can't just randomly square stuff, right? So you can square, like, if you have an equation, you can square both sides of the equation. He's like, shucks, right? But you can't just randomly square something, right?
So could we set it equal to 0 and then square it?
No, you can't just randomly set something to 0 either, right? So those aren't mathematical things, right? So, like, if I lend you $100, and when you come to pay me back, oh, now you owe me 100 squared, because I didn't like how the 100 looks, so I squared it. Like, you can't do that. You just change the value of the thing, or just set it equal to 0. Now I owe you $0. Yeah, you can't do that, right?
Do you multiply it by, like, that whole bottoms thing? Like,
what bottom thing?
That whole, like, the square root of 1 plus 3x minus 1, like, over the square root of 1 plus 3x, and then
yes, you're getting there. So what is it? So now you see you're jogging your memory.
Yeah.
So again, I don't do anything randomly. like, even when I'm here messing with you guys, just asking you questions and poking at you, there's a method to the madness. I want you guys to start thinking, because stuff is going to start coming back. What is that thing that she's thinking about? Does anyone remember what it's called?
The conjugate.
The conjugate. So she's thinking about the conjugate. Now, what is the conjugate of that guy?
I think it's the square root of 1 plus 3x plus 1.
Plus
over-
1.
Yeah.
Right. Now, so, and what we do is, so what I'm going to do is, you know what? That thing is not great in the bottom, so I'm just gonna multiply the bottom by that, right? So can I just extend this and do this? And then just simplify that?
I'm going to go with no.
Yeah. See, Luke is like doing the social engineering thing on these now. He's like, you know, that tone in his voice. He's definitely trying to bait me here.
Yeah.
Like, he's like, I'm going to go with a no, Jhevon. Next time I'm going to be all more excited. Oh, that's awesome. This is what we're going to do. We can do this, right? Okay. No, you can't do that. Why not? Again, for the same reason, right? You can't just randomly divide something, right? I owe you $100. You can't just randomly, you know what? Now I owe you 20. You can't just randomly put something in the denominator without changing the value, right? So what do we do there? Remember how we dealt with this scenario way back in algebra class when we were all young and free and carefree, is you have to multiply and divide by the conjugate. That way you're multiplying by 1, right? You're multiplying by something divided by itself. So you're not actually changing the value. So yeah, if I owe you $100, you can multiply and divide by 5. Yeah, that's still the amount of money I owe you. It doesn't change anything, right? So you multiply and divide by the conjugate. That is the strategy here. Okay, so now when I multiply by and divide by the conjugate, what happens to the denominator? What does it become? There's a long way to get to the answer, and there's a short way to get to the answer. And whenever possible, we prefer the short way. So focus on the denominator here. What does that remind you of? What does that look like?
Difference of squares.
Difference of
It's
squares.
difference of squares. So what is the result of such a multiplication? Right, like I have a minus b times a plus b. What does that become?
A squared minus b squared.
A squared minus a squared minus b squared. You square the first guy, which gets rid of your radical, the thing that was the problem, minus you square the second guy, right? Now, of course, you could multiply out and you write out all these multiplications with all these radicals. You're wasting time, though. The whole point of multiplying by the conjugate is to take advantage of the difference of squares, right? You have a radical, you have 2 terms and a radical. All you do is multiply by the conjugate. The reason is it invokes the difference of squares formula, so I can just square each individual part. So it's not like I can just square this whole thing. That's illegal. But if I multiply and divide by something like this thing, it allows me to square the individual parts, which is effectively just as good, right? So difference of squares happens in the denominator. So that is how we're going to get the new denominator. That's the whole point of the conjugate, right? To invoke a difference of squares formula or a difference of cubes formula or something like that. Which is why the conjugate for a cube root is actually a lot more messy than this. It's actually not the same thing. Conjugate for a cube root has 3 terms. Conjugate for a 4th root has 4 terms. Conjugate for a 5th root has 5 terms, etc. Conjugates
do that to us?
Huh?
Are you gonna do that to us? Like, are you gonna test us and like throw in the cube? Would you do that?
Probably not. No. He's like, stop giving him ideas.
Very good.
She needs to know. She's like, what am I up against here? Like, no, probably not. In the other class, probably. And in pre-calc class, when I would have taught them this, I would test them on that for sure. So difference of squares, I probably wouldn't do that for you guys though. I won't do that for you guys. Difference of squares in denominator. So now, what happens to the numerator? Well, nothing. You just kind of leave it as that times this. Right? So now what happens is you're going to realize that the ones get canceled. They kill each other, 1 minus 1. And so what we're going to be left with here is 3x in the denominator. Now you're going to realize, well, I still can't plug in x equals 0, but hold on. Now I can cancel the x's, all right? Because now things are separated by multiplication in the top and bottom. So now I just have 1 plus 3x plus 1 all over 3. And now I can actually plug in 0. It's 2/3. Strange. So yeah, notice here, when I plugged in 0, so here's something that I mentioned like the first 8. So notice here, when I plugged in 0, this actually approached 0 over 0. And you're like, what? What is that, right? And there were times when we approached 0 over 0 and it does not exist, like what happened up here, right? This guy approached 0 over 0. What does that mean? Infinity? No. In this case, it means does not exist. In this case, it means 2/3, right? Division by 0 is very crazy. Even when you're doing limits, right? We're not actually dividing by 0, remember? We're getting close to dividing by 0. But what happens when you do that? It's all a toss-up. It could be literally anything. Like, could be 7, could be pi, could be e squared over 9. Like, it could be anything, right? So division by 0 is something that you approach very, very carefully, even when you're doing limits and we're not even actually dividing by 0. Things can, the answer can be very peculiar. Okay, let's move on. So for these, kind of crazy, but I'm going to give you, I'm going to tell you, well, I'm going to do them the responsible way, right? So some students know that they're when they have a problem like this, I mean, probably not most, but maybe like 4 out of 10 math teachers who give you this problem are going to expect you to do it. You have to do it this way and show your steps and show where you're going to get. But I'm going to actually teach you guys a shortcut for these guys. But first, I'm going to show you the long way so that you can see why the shortcut I'm going to give you works, right? But then there are going to be some, depending on who you're dealing with, might expect you to actually write out the long way. So here's something that we can do. So here, this looks crazy. Simplifying, plugging in, all that stuff doesn't work, right? Can't plug in, x is infinity. What does it even mean to plug in infinity, right? I'm gonna get infinity over infinity. I don't know what that is. Simplify, yeah, good luck, right? Like, am I gonna factor that? Not today, right? Graphing, yeah, I don't wanna graph that. And I don't wanna plug in a table of values, right? So what do we do, right? So it turns out that this is actually a very special situation. Here's what I want you to notice. First, it's a limit at infinity. Okay, so that's the first thing. Okay, so what we're going to do is we're actually going to simplify, right? Because one, plug-in doesn't work. But this was one of these weird simplifications where it's like, is it really simplifying? Because I wouldn't do this under normal scenarios, but it turns out to be a very helpful maneuver in this scenario. So it turns out I am going to simplify this in a convenient way, which is kind of a weird thing to call it, but I'm gonna do it anyway because, you know, I'm Jhevon, I'm the teacher. I can do whatever, it's my class. Okay, so here's how we can do this, right? I am going to divide each term by the largest power of x in the denominator. And it's always going to be the denominator. Okay, so I identify the largest power in the denominator. Notice that that is x to the fourth. And I'm going to divide everyone by x to the fourth. So I'm going to go, okay, 4 over x to the fourth plus x over x to the fourth minus x cubed over x to the fourth, 2x to the fourth over x to the fourth minus 3x squared over x to the fourth plus pi x over x to the fourth plus radical 2 over x to the fourth, right? Is that legal? Yeah, because really what I did was I multiplied by 1 over x to the fourth divided by 1 over x to the fourth. So it's kind of the same idea as I'm doing here, multiplying and dividing by the same thing. I'm not actually changing the values, right? So when I divide the top and bottom by the same thing, it's essentially equivalent to multiplying by 1. It's legal, right? So what I'm actually doing is divide each term by largest power of x in denominator. And it's always the denominator, right? You always say the biggest guy in the denominator. Okay, that's going to be the first thing. So now I'm going to simplify this stuff. Well, 4 over x to the 4 doesn't really simplify. This guy goes 1 over x cubed. This guy would be 1 over x. This is going to just be 2. That's going to be 3 over x squared. This is going to be pi over x cubed. This is going to be radical 2 over x to the fourth, right? Now, on one hand, you might say, well, that doesn't really look simpler than that guy. But remember, limits are super nice. You see this guy right here, I can actually distribute them across the numerator and denominator, and then distribute it across the sums in the numerators and denominators, because limits can do that. Now, if you look at each of those individuals, can you tell me what's going to happen?
Oh, most of them just become 0.
Most of them become 0.
The rule.
Right. So that is pretty neat, right? So somehow this little simplifying trick actually works out in our favor, because now you're going to realize that hey, that's going to go to 0. 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 Most of these guys actually go to 0 by applying the limit properties. I'm applying 2 limit properties here. I forgot what I numbered them. So I'm applying the fact that I can distribute the limit across the sum. So that's property 3, as well as I can put the limit in the top and bottom. So what I do is I put the limit in the top and bottom, and in the top, it distributes across the sum, and in the bottom, it distributes across the sum. So this is by limit properties 3 and 5. I can do this, right? So that's legal because I'm equivalently multiplying by 1. This is legal because of limit properties. Now I'm in this situation where it's like, hey, most of these guys actually go off to 0. So it turns out that this is 0 over 2, which is 0. Ah, isn't that neat? Okay. That is how you would show your work for this problem. But of course, I'm actually going to give you a better way because efficiency, right? Let's actually look at this one. Turns out it's a very similar scenario as with f. So here's another one. So again, 1 can't plug in. 2, simplify? Well, not really. Then you note, gasp. Boom, you know it's a limit at infinity. Why does Jhevon keep pointing that out? Okay, so this tells me, you know what I'm gonna do? I'm going to divide the top and bottom by the highest power of x in the denominator. Always the denominator. That's x cubed. So I'm gonna have 4 over x cubed minus 6x5 over x cubed, 7 over x cubed, plus 2x cubed over x cubed. So that's going to be 4 over x cubed minus 6x squared over 7 over x cubed plus 2. This guy's going to go off to 0. This guy's going to go off to 0. What is this guy going to go off to?
Infinity?
Infinity, right? So this part goes off to infinity, which means this limit here is approaching, well, negative infinity, because there's a negative sign in front of it, divided by 2. What's half of negative infinity? Still negative infinity, right? So boom, that's the answer, clearly. Right? So this is actually an infinite limit at infinity. Right? And I can see that clearly by doing this trick of dividing the top and bottom by the highest power of x in the denominator. Here's another one. Okay. Same deal. You go, all right, can't plug in because you can't plug in infinity. It doesn't mean anything. So now you start thinking, simplify. And like, how do I simplify that? But then I notice, hey, that's a limit at infinity. So I know what I'm gonna do. You know I'm gonna do? Okay, so here, what I'm going to do is I'm going to divide by the highest power of x in the denominator, which in this case is x cubed. Okay. So that is going to simplify into, well, 17 plus 3 over x plus 1 over x cubed over 5 over x cubed minus 1 over x squared minus 2. Now, again, why was it important that it was a limit at infinity? Because these guys go to 0 under that condition, right? Otherwise, it would not have, and I would be in a different situation. So those guys go to 0, but 17 is 17, and minus 2 is 2. And me distributing the limit across the top and bottom and then across the sums tells me that, oh, I get minus 17 over 2 as the answer here. So that's the answer. Right? Interesting. Now, it turns out that there is a special technique hidden here, which is the second special technique I'm going to tell you. It turns out the above represent all possible scenarios for a special case. There's a special technique hidden here. Super duper special jutsu. Okay, so this is the technique. Special technique. For limits at infinity of rational functions. Okay, which is what you'll notice these last three examples where I did this thing all fall into that category. I had a rational function and a limit at infinity. All right, so some definitions are in order here. Pre-calc is potentially a long time ago. So recall rational function. What does that mean? This is just a ratio of polynomials. Yeah. Oh, gosh. God. Can't let anyone know I had trouble writing the word polynomials. They'll eject me from the Math Society. Okay, ratio of polynomials. So this means it's a function that looks like, you know, P of X over Q of X, where P and Q are polynomials. We know what polynomials are: X to whole number powers, sum of a sum of X to whole number powers with some constant coefficients in front of them, where P and Q are polynomials. And of course, Q not equal to 0. So we're assuming that we're not looking at where the polynomial hits 0. So that's called a rational function, right? So those are the guys that they're not rash. They don't just go off and do whatever. They're not crazy. They're very rational. They think through stuff before they do them. Another thing that you'd need to know is what's called the degree of a polynomial. The degree of a polynomial P of X, which I might denote by shorthand, degree of P, right? So this is the highest power. That appears, right? So appears means has non-zero coefficient. Technically, I can take any polynomial and add 0 times x to the million, and oh, now the highest power is a million. No, non-zero coefficient. Right, so some quick examples to make sure you know that. So if my P of X equals 2 minus 3x plus 7x squared, the highest power that appears is 2. This means it is a degree 2 polynomial, otherwise known as a quadratic polynomial or a second degree polynomial. If I have 17x to the 9 minus 2x cubed plus 7x minus 1, this is a degree 9 polynomial. Why? Because the highest power is a 9. Okay. Another definition, and then I'll tell you the secret special technique and let you go. But I think you need to know another phrase in order for that to make sense. So the leading coefficient this is the coefficient of the highest power term. Okay, So if I were to use these examples here, copy. And instead want to point out the leading coefficient. And just to make things interesting, let's make this a negative because I do want to emphasize something. So in this scenario, leading coefficient is -7, right? That is the guy, that is the coefficient of the term with the highest power, right? And I wanted to emphasize that you would take the minus with it, right? So -7, you need to bring the negative. It's not just the 7. In this guy, that's the guy. So this is the leading coefficient here. So sometimes students think leading coefficient is just the coefficient in the front, it's the coefficient in the lead, but it's not. It's the guy with the coefficient of the guy with the highest power, because the standard way to write a polynomial is in descending power order. So if you rearrange it, it's always going to be the leading coefficient. But really, it's the guy in the highest power if it's rearranged in some other way, right? Okay, so now here's the statement of the technique. So this would apply in step 3 of our process whenever possible. Whenever you have a limit of this form, the limit as x approaches plus or minus infinity, it has to be an infinite limit. What I'm about to tell you does not apply if it's not a limit at infinity of p of x over q of x. So we're looking at a thing of this form where p and q are polynomials. Then it turns out that only one of 3 things are possible, right? And I've illustrated all 3 things in the previous examples. One possibility is the following. The answer is going to be 0. This will be the answer if the degree of q is larger than the degree of p, right? If the highest power on the bottom is bigger than the highest power on the top, you're always going to get 0. You don't have to think about it. This is called bottom heavy, right? And we call it that because, as far as I'm concerned, that's showing your work to me, right? So if you tell me that's the answer, you write bottom heavy, to me, that's showing your work. You don't have to go through that whole thing where you're dividing everybody and blah, 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 right? Another scenario is you would get infinity as the answer, plus or minus. You have to pay attention to the signs to know which. This happens if the degree of q, the degree of p is bigger than the degree of q. So if the highest power is in the top, it's going to go off to infinity, right? It turns out that the last scenario that you would end up within is it's going to be the leading coefficient, and now we know what that is, of p divided by the leading coefficient of q. And that happens when, and this one we call top heavy. And that happens if the degree of p is equal to the degree of q. And we will henceforth and forevermore refer to this as the ratio of leading coefficients. Okay, and so I do want to emphasize this is not a technical term. That's just what I'm allowing you to call it. Okay, what does that mean for us? It means that these last three examples I gave you, you could have done them more efficiently. Not in every math teacher's class, but in my class. There are some who would rather see you actually write out this whole division process. Me, no, not so much. So it turns out that you don't, if you have this, you don't have to go through all this because the answer is going to be actually a lot more straightforward. And it's going to be something where it's like, you would be able to know what the answer is with doing very minimal calculations. So we're going to redo all these three problems in less time than it took us to do one of them previously. So here, notice that I'm in that situation for the special technique. What do? Identify the largest powers. In the top, that's this guy and that guy. Notice that the largest power in the bottom, this is 0. Why? Bottom heavy. Done, right? As far as I'm concerned, you showed your work. Move over here. We're at a limit at infinity of a rational function. What do? Identify the highest powers. What is going on? Well, the highest power is on the top, so I know this is going to be infinity plus or minus. But which infinity? So this one, as the technique suggests, you really have to pay attention to the signs, right? So you're going to make sure you choose the right sign. So you're going to go over here and you're going to look at, well, what's that going to happen? Well, that was x to the 5th? I feel like we did the wrong thing. Okay, so what's going to happen? Here, you're going to have negative infinity. Well, you're going to have positive infinity on the top because you have x to the 5th, you plug in a negative number, it stays negative, multiply by a -6, you get a negative, divided by, in the bottom, you're going to have a negative infinity, right? So the infinity parts you don't actually care about. You actually just care about the signs, right? So this, you just know it goes to a positive divided by a negative, which means it goes to a negative, which means the right symbol to pick is the negative symbol. So you can know that this was just negative infinity. And then you just write down to show your work, top heavy. And that's it, we're good after that. So for this one, same deal. You see something like this, identify the, I was messing up. Identify the biggest guys. It turns out they're the only ones that matter when we go up to infinity. Maybe I'll talk about that later. Now you'll notice that the highest powers are the same on the top and bottom. So you just take the coefficients of the highest powers and divide them by each other. And that's a ratio of leading coefficients. And that's showing your work. So we can do all of those. I don't know why that thing is appearing. Anyway, whatever. So yeah, we'll end there. That's the end of limits for now. We will do a few limit techniques in the future, but for now, that's all you need to know about limits. We'll end there.
Question.
Yeah.
Online, I saw that like the homework, it's all for chapter 1. Did you like me to put chapter 2 or?
Yeah, you don't see that visible yet? I'll make sure to put that in.
No, it's only chapter 1.
Okay, I'll fix that. Okay,
thanks. Also, and I don't know if you uploaded this class video for
No, I'll put that in. It's you're supposed to be able to see the other stuff. Okay.
Yeah, but also last class though, I don't think you uploaded like this class's YouTube video for last class.
Yeah, I had technical issues. I uploaded that this morning. So you should see it now.
I just used the other class's video to get these problems. I don't know if like anybody.
Okay. Yeah. All right.
Yeah.
That's fine. So yeah, that's my bad. But we'll end there. Thank you for your attention. Thank you for sticking around. But we'll end right there. I'll see you guys in the next one. Ciao.